Nice. Hope you enjoyed that cybersecurity and AI session that we just had. Up next, we have more AI coming, believe it or not. And so this one is all about pushing the limits of computing to keep pace with AI's growth. Join us as Naveen Verma, who is co-founder and CEO of EnCharge AI, as well as a professor at Princeton University. He'll be tackling the compute bottlenecks that are holding back progress, and he'll unveil what the next generation of hardware could bring. Naveen will dive into how new edge and cloud infrastructures could break through the silicon ceiling and unlock efficiency gains that go far beyond the traditional computing that we have today. Please join me in welcoming Naveen and our moderator, NPR's Bobby Allyn, to the stage.
So, wanted to kick things off by talking about generative AI and compute and the very moment at which the situation seemed to change in terms of, oh my God, we have all these really cool generative AI and other sophisticated AI tools. Do we have enough compute to power them? When did that moment become crystal clear?
I think that moment was actually a little bit of something spread out over time. I think there's a couple of critical moments that led to that. The first was, I think, a broad recognition that generative AI is something extraordinarily powerful and useful. And I would say the landmark moment there was the emergence of ChatGPT in late 22 sort of time frame. Then we went into a period where we got this powerful tool. What do we do with it? What is it going to be good for? And people, a lot of the industry went into this phase of doing proof of concepts really through much of 2023. During that period, there was some use cases that emerged that seemed to be very useful. And so then there was a move to try to deploy those at scale as real product services. And it's at that instant when you started to do that a lot of the unit economics became exposed, a lot of the problems became exposed, and real questions started to arise about how we're going to make generative AI sustainable as a useful mass market kind of technology.
So a lot of this audience probably knows what Moore's Law is, but can you just give us kind of the broad overview of what Moore's Law is and how next generation AI has really sort of confronted some of the underpinnings of Moore's Law?
Yeah, so I think there's two critical laws to know about. One is Moore's Law, which gets a lot of attention and understanding. And it's basically the idea that we're going to keep shrinking our transistors. And the reason that that's important is it becomes the economic driver of the semiconductor industry. Basically, you pay for silicon wafers, and if you can shrink your transistors, you can fit more of them on that silicon real estate. That makes the cost per transistor go down exponentially, and presumably with that, the capability of compute go up exponentially. So Moore's Law has really been an economic driver. There's another important law, which is something called Dennard scaling, and it's a very technical law, which says that it turns out if you make your transistors smaller, it has this economic benefit that Moore's Law relates to. But it also makes your underlying technology, your transistors, better. It makes them more power efficient, it makes them faster, it gives you more of them so you can build more and more complex architectures. It turns out that both of these laws have saturated in the last, I would say, 2 to 3 decades. And so we in the semiconductor industry have a real problem to confront about how do we continue to push both the economics and the capability of compute that these two laws gave us. It's an important thing to note that even in the best of times, when Moore's Law and Dennard scaling were full bore, they still didn't deliver capability at the pace that AI has demanded today. So even in the best of times, we really didn't have a technology that met the scale of what we're seeing in AI today, and yet, of course, now we face the two-sided problem where also these laws have saturated.
When people talk about the winners and losers of the AI boom, I mean, the first company that comes to mind is NVIDIA, obviously, right? And I mean, last I checked, I mean, based on their market cap, they're like the most valuable company in the world. And I think when I talk to people about NVIDIA, there's this misconception that they're designing and producing chips, but in fact, they're just designing chips, and they send those designs largely to Taiwan, to TSMC, to create the chips, right? And there obviously has been this whole movement to try to onshore, make domestically some of these really advanced AI chips, but right now Taiwan just really has an incredible, almost global monopoly on the most advanced silicon chips that are powering generative AI. How did we get to this situation? Some people ask, why isn't Intel creating these chips?
Yeah, it's a great question, and I think the answer comes from two directions. The first is, quite frankly, we started to think about manufacturing of silicon chips as any other kind of manufacturing where, sort of the leverage in being able to deliver very advanced products didn't lie in the manufacturing, but rather in the design. It turns out that that's not true, and really it's something that the semiconductor industry and kind of the technical leaders in this space have known, and so it was a real risk, but one that kind of just followed the momentum of a lot of manufacturing. And so you saw a lot of manufacturing move to Asia because of cost pressures and things like that, and Taiwan, I think, really met the moment on that regard. So that's the first thing. The second thing, quite frankly, is to TSMC's credit, they've been incredible innovators in this space. I think what they've done is contrary to a company like Intel, which was perhaps the previous leader in semiconductor manufacturing. See, Intel had a kind of internal customer, a big internal customer. They were building their own processors, and then they were also manufacturing those processors. And when you have that kind of dynamic in a category where innovation and very deep technical breakthroughs are critical, this can become a problematic burden. They weren't able to keep the pressure on some of the technical innovation that was needed to maintain that leadership. I think TSMC, on the other hand, had a very aggressive plan to engage really important customers. They took on really key strategic customers like Apple, and they took on NVIDIA, and they took on AMD, and those became important teaching customers and drivers, which really helped to sort of motivate and force innovation within TSMC's kind of infrastructure towards creating what now is clearly the industry-leading technology. So I think it's really these two-sided dynamics that has led to TSMC being where they are today.
Obviously, TSMC having fabs, along the Taiwan Strait in this very geopolitically tenuous region puts the global economy kind of teetering in the balance of that, right? And so as long as China keeps sort of ramping up its antagonism there, a lot of China experts and Taiwan experts are really worried it would somehow affect supply chains for silicon chips. So just putting a pin in that, but sort of looking at the US and looking at innovation in the US, how does it hold us back that we can't be producing the same volume and the same advanced chips that Taiwan is producing, and what steps have been made to try to counter that?
Yeah, so I think there's very broad recognition that securing that semiconductor supply chain, especially at the very bleeding edge of semiconductor innovation, is critical. And I think that the truth is semiconductors are complex enough systems that one needs to take a very holistic approach to how that's going to look going forward. And I think that countries like the US and others are doing that, so that's a very good thing. I think that when we think about that complexity, it makes it both challenging, but it also opens up many different opportunities and levers to maintain this kind of leadership. So I think the advanced manufacturing of individual silicon chips and silicon wafers now becomes only one part of it. It's an important part, and it has to be part of the strategy, and that's why there's, in all of these initiatives to bring manufacturing onshore, the engagement of TSMCs and trying to bolster and accelerate the development and progress of Intels and things like that to do that advanced semiconductor manufacturing of the wafers. So that's part of the strategy. But I think the important question is also to ask, in a world where we've seen so much innovation so quickly, what is the future of AI systems, or I should say rather semiconductor systems, going to look like? And the truth is, it'll be a combination of things in addition to the manufacturing of those advanced wafers. It'll be the integration of multiple different kinds of semiconductor technologies. It'll be various kinds of system concepts that combine memory and interconnect and compute. And so I think when you start to have all of these different dimensions, now you start to open up a range of other opportunities where, look, bringing that advanced wafer manufacturing onshore has a lot of inertia and challenges. We need to address it, but we should also start developing from the start these other aspects that are going to be critical. So I think part of how do we catch up is really a story of, yes, bringing back advanced manufacturing of the wafers, but also incubating and fostering the ecosystems of the future that will be needed for advanced semiconductor systems.
So both as an academic and an entrepreneur, as you've been mentioning, sort of examining the full stack of chip production and manufacturing. What problem are you hoping to solve and scale? And if you could sit down with top AI policy leaders in Washington, based on all of your research, what would be your clear message to them?
So, I mentioned that we've had, in the best of times, these very powerful laws, Moore's law scaling and Dennard scaling, the engines of the semiconductor industry. I also mentioned that if you look at the trajectory that AI has been on, it far outpaces what those laws were giving us in the best of times, in their golden ages, right? We've seen something like a 10,000x explosion in AI compute requirements and data requirements over the last decade. Moore's law, Dennard scaling never gave you that. And so I think the critical message here is, when it comes to a technology like AI, of which we're seeing such profound importance, we need to really think about, fundamentally, what kind of compute is being done there, and recognize that the kind of compute we've been doing doesn't align well to that. It doesn't give us a sustainable pathway towards that. And this is certainly how somebody like me gets engaged. Looking at AI, drilling down to what the fundamental compute is, you can start to ask questions like, what is the fundamental compute technology that's going to align with AI and make it sustainable? And that's really how I got involved, and we developed a technology in my lab at Princeton University, that we've been researching for many, many decades, something called in-memory computing, which is unique in that it solves both compute efficiency bottlenecks, which we face in AI, but also data processing and intensity bottlenecks, which we also face in AI. It's one of the very unique architectures that enables us to do that. So it's an example of something that, by looking fundamentally at the ways in which AI is stressing computing systems and really fundamentally not aligned to the computing technologies we have, for us to reimagine what those computing architectures should be. And I think that the broader message here is, we need to deliver these technologies into the market and the ecosystem because the sustainability, the cost viability, the unit economics of AI, which we all have great hopes for, relies on it. And so I think we really need to think collectively about how to unlock and enable that sustainability of AI, and this technology plays a critical role as one thinks about sort of the ecosystem and policy questions around it.
So when it comes to trying to prepare ourselves to have the compute for next-gen AI, something that often comes up is just how energy intensive this compute is going to be. Are there ways that you've sort of thought about in terms of trying to mitigate that so we're not killing the planet as we're innovating with next-gen AI?
And that's, once again, what makes this a fundamental problem, right? Because the amount of energy, which ultimately is the amount of power that you consume to do compute, is based on the fundamental physics of how compute is done. And there are opportunities for breakthroughs here, including the one that we've developed and been researching for many years. And I'll give you one example of this. It turns out that there's two approaches to building electronic systems. There's something called digital compute and analog compute. Digital compute is what we've done all along, and basically says, hey, listen, you have signals, but let's pretend that those signals are either a 0 or a 1, and nothing in between. And that's a good thing to do, because if you have 100 billion transistors on a chip, which we have today, all of these can have some noise, and if they have noise, you're going to want to have big signal separation so that all 100 billion of them work. And that's the reason we build digital systems. But you can kind of envision here, by restricting ourselves to these two signal levels, we're leaving a lot of representation of data and signals on the table by not representing those intermediate values. And that's precisely what analog compute does. The challenge with analog compute is now it's susceptible to noise, and you still need your 100 billion transistors to work. And so we need fundamental breakthroughs around how, for example, we can make more efficient technologies like analog also robust to noise scalable to these 100 billion transistor systems and well beyond as we look into the future. That's really what, as an example, my research at Princeton was deeply focused on, where we had some breakthroughs about a decade ago, which have now led to the technology, for example, that we're commercializing at EnCharge.
Yeah, I think consumers are maybe a little fatigued with LLMs at this point. They were very exciting a couple years ago. Now we're like, okay, we get it. And there's been a lot of use cases that have, really gotten entire industries very excited. But from the consumer level, there hasn't been this sort of like killer AI app yet. Why not? And what's holding us back from that?
I think at the end of the day, some of the most profound drivers of things like killer apps and adoption by society is the economics. And those are just the realities. I mean, we talk about energy efficiency and we all value our planet and climate sustainability. But often when it comes down to sort of do the unit economics work, those are the drivers that make things happen. And quite frankly, I think what we've seen so far is that there's a lot of potential for AI, but to see that killer application, and not just the one killer application, but an entire suite of killer applications or an entire roadmap of killer applications, you need to have the economics make sense. Yeah. That then starts to kick off a process where we have innovation that drives economic growth, that drives further innovation. And so what's really holding this back is the unit economics for a lot of AI just doesn't make sense today. A lot of it has to do with the power efficiency problem and the deployment of AI in data centers, which have, as a result of the operating expense derived from power and cooling costs, kind of poses barriers to those unit economics. So I think we really need ways to make AI unit economics make sense in order to start to see an innovation cycle take hold, to then start to see the creation and broad-scale deployment of many killer apps.
And do you have any sort of like theoretical use cases that you'd be excited about?
I think that we have a lot of examples of use cases where we can see a lot of great utility. I mean, I think as you think about the very advanced multimodal personal assistants, yeah, as we think of very advanced agents, one can very quickly start to envision how these sorts of systems can dramatically improve the efficiency of enterprise use cases, consumer use cases, everyday kinds of use cases that we all care about. And I think the fact that you start to incorporate the range of data from text data and visual data and so on really allows us to imagine a lot of such use cases. You take that one step further and you start to think about the vertical integration of these sorts of systems, personal assistants and agents, into the healthcare space, into the legal space, into the public safety space. And I think you can very quickly start to see a lot of different applications that would be of very high value. Once again, the challenge is that these AI systems today that have that profound level of capability also have profound level of compute requirement, which turns us back into that unit economics challenge.
So if we're sitting here on stage in Lisbon 5 years from now, having a conversation about AI compute, what might we learn by then, do you think?
I think that we're going to see a lot of innovations, and I think that we are going to see through that innovation the start of these cycles which will enable killer applications to emerge. I hope what we'll start to see in 5 years is not just the emergence of a killer application in one particular direction or another, but we'll start to see the emergence of several killer applications, and then from that we'll start to see what kind of platforms are needed all the way down the stack, software down to the hardware, that can enable more and more innovations and innovators to engage. I think the lack of some of those killer applications today hasn't given us a clear picture of how to build this entire infrastructure to enable broad-scale innovation. I do think that we will see that in 5 years. I mean, if you look at the kind of progress that's been made from disruptive technologies like the smartphone over a 5-year period, you've seen complete transformations to society. I certainly think AI has the potential to do that. What we really need to do is unclog, I think, some of the economic barriers.
Well, thanks for taking the time. I really appreciate it.
Appreciate it as well. Thank you.